So what I want to do is I want to talk about low-lying zeros of L functions. I'm going to concentrate on GL2 L functions. These are very interesting. It's enough so you begin to see some of the non-trivial behavior. I'm going to talk about random matrix theory, classical random matrix theory. It's not really used too much by number theorists today anymore, but it was very important in terms of the historical development, and I know several people are interested in just classical random matrix theory ensembles. The reason it's not used so much anymore is the notion of randomness there is from choosing entries randomly from a fixed probability distribution. As number theorists, we like to use Haar measure classical compact groups. There you have a natural notion of randomness that's just brought upon you, whereas when you're choosing the matrix elements, well, what distribution are you using? If you believe in some things in physics, that the laws of physics should look the same in different coordinate systems, that will actually force your choices to be Gaussian probability distributions. So, not surprisingly, this is a sequence of lectures I gave years ago at Michigan. One of the many nice things about the math department there, and it does hurt me a little bit as a Ohio State former professor to say this, is that they have very long talks. So you can split the talk into the non-technical part for everybody and the technical part for the very small subset. So I'm going to start with the non-technical part. Okay, so why do we want to study zeros of L functions? Well, because you're working with me this summer, I'm going to assume that you're highly motivated and you can read this slide later. But there's a variety of problems and they are connected to zeros of L functions. And it turns out that the distribution of zeros help us analyze and answer these questions. And in fact, what happens is the more you know about the zeros of L functions, the more you can say about these problems. So if you just want to prove the prime number theorem, that the number of primes up to x is about x over log x, you basically just need the zeta function is not zero on the edge of the critical strip. Real part of s equals 1. As you get more refined things, if you want to have what is the error term in counting the number of primes, then you need improvements on that. And instead of being non-zero just on the line real part of s equals 1, you improve to the Riemann hypothesis, that there are no zeros with real part greater than a half. Chebyshev's bias is the grand simplicity hypothesis that zeros of L functions are linearly independent over Q, because how could they not be? And so of course, this is actually false in the function field case where you can find situations where you have L functions where Chebyshev's bias, where GSH fails. This is useful in Chebyshev's bias in studying the propensity for primes to be more likely to be in certain residue classes than others on certain scales. Another one is analytic rank, adjacent spacings. This is related to things for the class number. Okay, so the goal is to determine the correct scale in the statistic to study. It actually takes a long time to figure out what is the right quantity to look at in terms of what encodes the information that you have and what is mathematically tractable. You will see the further you go in analytic number theory, the more it is combinatorics, and trying to find good ways through the resulting combinatorics. We'll see very similar behavior in many different systems. I'll discuss a little bit about the tools and techniques needed to prove the result. Depending on what family you look at, you're going to have to assume different technical things. You'll have different workhorse lemmas. What's fascinating is the actual calculations are different in number theory and in random matrix theory and physics. What's nice is you end up with the same answer, with very different calculations. So it becomes a great way to check your work and see, have you dropped a minus sign? I actually dropped a minus sign infinitely often in one of my papers. We were integrating by parts, the boundary terms canceled, and I was always doing it an even number of times. So fortunately, all the mistakes canceled. You will not find all of your mistakes, but hopefully you will find all the mistakes that matter. Talk a little bit, probably in the next version of the talk, about some new results on GL2 that I've done with students in the past few years. Alright, so the fundamental problem is spacings between events. So almost all of my work actually falls under this general fabric, from zeros of L functions to Zeckendorf decompositions. Here's a bunch of things you can look at. Energy levels of heavy nuclei, eigenvalues of matrices, spacings between primes, zeros of L functions. We want to know what rules govern how long we have to wait until we get the next event. And so the three big items in the proof is determining the correct scale to study, developing an explicit formula that relates what we want to study to what we can study. So we've already talked earlier about the eigenvalue trace lemma, and then use some kind of averaging formula to analyze the quantities that come into play. So without 3, 2 is useless. 2 just converts your problem to something else. if you've ever taken a class in combinatorics, that's essentially all combinatorics is. You want to study x, I know y. Does that help at all? Well, if you can connect x to y, yes. And that's the goal, is to try to connect these things and then have techniques that will help us look at the new formulation. Alright, so let's do classical random matrix theory in hopefully 10 minutes or less. So, in mathematics, physics, the three-body problem from classical mechanics is intractable. So what that means is if I take 3-point masses in general configuration in space and ask how do they evolve over time, we can't write down a closed-form solution. So whether or not Pluto is a planet is a function of human society. Whether or not Pluto will orbit the sun, a million, billion years from now, that's a question for mathematics and physics. And we can prove some general qualitative results about the orbits of planets, but to exactly write down where things are, we don't have good exact formulas for that. Think of it as trying to integrate the Gaussian, the normal density. We have series expansions for it, we can approximate it very well, but we don't have a nice closed form solution. The definition of what is a closed form solution, it's a little bit open to discussion. Is sine of x a nice function, yes or no? Well, it's an infinite series expansion that we've collected and given the name sine. So if I tell you, we have the sine of this, I'm really sweeping under the rug that I have an infinite series, and I'm just calling it sine of x. So you've got to be very careful as to what you mean by a closed form solution. Just giving something a name and saying, ha-ha, that's not acceptable. All right. So heavy nuclei like uranium with over 200 protons and neutrons is far worse than just 3-point masses. And so if we can't even understand 3-point masses, uranium is intractable. It turns out that the sheer complicated structure, the fact that we have 200 things, is actually going to help us. Now, how can we get some idea of what's going on? Well, and this will be useful later in number theory, is we can shoot some high-energy neutrons into the uranium nucleus and see what comes out. One of the best quotes I ever heard to describe physics was, you have these super colliders. And let's say you want to understand how a grandfather clock works. So you take two grandfather clocks and you accelerate them 2.9999 times the speed of light, and you smash them together, and you look at all the cogs and gears that come out, and from that you deduce the workings of a grandfather clock. This is what the physicists do. And they do it very well, and they can deduce a lot of information. We will see analogs of this in number theory, but our idea is we shoot high-energy neutrons into the nucleus, we see what comes out, that gives us some idea of the energy levels and the structure, but not a complete picture. What's going on here? Well, we have this functional equation which is coming from quantum mechanics. So H is a matrix, its entries depend on the system, Cn is the energy eigenstates, En is the energy eigenvalues, and as I've said before, H is infinite by infinite and we don't know any of the entries. And so we are not going to get far diagonalizing an infinite by infinite matrix where we don't know any of the entries. So Wigner's great insight was to basically say, screw this, let's look at something similar to this but far more tractable. And so his motivation was statistical mechanics. So if we want to calculate a quantity such as pressure, we want to know how many molecules hit a wall in a given amount of time. So we can look at each possible configuration. For each configuration we calculate the quantity such as pressure, and then we average over all configurations. So the hope then is that a typical system will be close to the system average. Most of the time that will be true, and frequently you have central limit type theorems going on. So what he will do is you'll look at a large n by n matrix, and then the matrix might have additional symmetries depending on the physical system. Maybe it's real symmetric, maybe it's complex summation, and then you try to calculate the eigenvalues for a specific matrix. So this leads to the notion of how do we choose our matrices at random. The number theorists for the most part don't like this anymore. We like to use Haar measure. But this is how the physicists really begin the subject. So let's say I have a real symmetric matrix, so A equals A transpose. I choose the main diagonal and everything above. The low is filled in by symmetry. And the probability of my matrix A is the product of the probabilities. And so this means the probability that I choose a matrix where the ijth entry is in this box is just going to be the integral over all the independent entries. And now I can calculate a lot of quantities related to this, and I can try to use this to understand the eigenvalues. So a little bit more explicitly, let's let delta denote a Dirac delta functional. So essentially it's a point mass located at x naught. So the integral of f of x times the delta function is just f of x naught. So I'm going to put a point mass of size 1 over n at each normalized eigenvalue. And we'll talk a little bit later as to why we want to do 2 square roots of n. The two quantities like this are never important. That's just to adjust a little bit the scale of what's going on. It's going from meters to feet. The really important factor is the square root of n. Is to try and figure out what is the correct scale to study the eigenvalues. So this is going to essentially assign a mass of 1 over n to each normalized eigenvalue. If I integrate from a to b, this tells me how many normalized eigenvalues I have in the window from a to b. The kth moment is I will just integrate x to the k times this, and because it's a delta function, I'll just get lambda I of a over 2 root n to the kth power, and that's just the trace of a to the k. And so Wigner's semicircle law, this is not the most general case, but it's a good enough case, is if you have n by n real symmetric matrices, choose the entries independent identically distributed random variables, mean 0, variance 1, find out higher moments, then for almost all a, as n tends to infinity, the measures we have here that count how many normalized eigenvalues we have converge to the semicircle. And so the key idea in the proof is the eigenvalue trace line. And we'll see analogs of this when we get to number theory. The goal is to convert what we want to study, the eigenvalues, to what we can study, the matrix elements. It's the matrix elements that we're choosing randomly. That's where we're going to have information. In number theory, we will have an L function, and we will have the coefficients of the L function. We'll know stuff about that. We'll have formulas for their sums. We want to convert from that to knowledge about the zeros. So the trace of a to the k is the sum of the eigenvalues to the kth power. Trace of a to the k is just this product of the sums of k terms. All right. So to get the correct scale, the trace of a squared is the sum of the eigenvalues squared. So it's aij, aji. Each one of these is roughly going to be of size 1 because we're choosing them from mean 0, variance 1. This is essentially the expected value. This is essentially the variance. So this is going to be of size n squared. The fluctuations are going to be much smaller than n squared. Good exercise to see what that is. So the sum of the eigenvalues squared is about n squared. Illegally taking the square root inside the averaging tells us that the eigenvalues are going to be of size square root of n. So this tells us how to look for things. So that was the first of the 3-step program. Find the correct scale. We've already got step 2. Find an explicit formula to relate what we want to what we know. And then step 3 is just the averaging. So now what we have to do is we're going to look at the average kth moment. And so the hope is that if everything is nice, if I know a sequence of moments that uniquely determines my probability distribution. This is kind of like the hope that Fourier coefficients determine a function, or Taylor coefficients determine a function. Sadly, these are not always the case. You can have 2 functions that have the same Taylor series, but are not identical. But maybe if everything is nice, and then there are some results from complex analysis that will help us, if I know my sequence of moments and it satisfies certain conditions, it will uniquely determine a distribution. And so now I want to calculate the average kth moment. And then I'll look at the new distribution that's essentially the average over everything. And then I'll try to play some games to show that each individual measure is close to the system average. So there's some black box results from complex. Well, what it comes down to is using the trace of a to the k, which is the sum of the eigenvalues, which is what I got to the kth power, is the trace of a to the k. I'm now left with this integral. This is a polynomial in the matrix elements. So I just have to evaluate this integral. And then I need to show that I get the sequence of moments. The sequence of moments determine a nice distribution. Most matrices will then be very close to this, and their resulting probability distributions will be close. So you need to control this somehow. So here is a completely misleading special case. Let's look at the second moment. So I want to calculate the trace of a squared. That's the sum of a. I have no idea why I wrote ji, but since I've always pasted it, it has stayed like this. So I have aji squared, and I have all the different probabilities of my elements. Well, there's essentially 2 things that happen. I can pull the sums outside the integral, and I have the term when I have aij hitting the paij, and then I have all the other pairs. Because I have a probability distribution, all of these integrals are 1. This is the variance of my random variable. That's also go to 1, so I get 1. When I put in this factor here, I get 1/4. There's the second moment. This makes the subject look a lot easier than it really is. The higher calculations here, the higher sums when I have the 4th moment, the 6th moment, the 8th moment, there's a lot of combinatorics that arise in terms of trying to figure out what the contribution is. and figuring out how things match. And so, for instance, the higher ones over here, if I look at something like this, I've got a bunch of A's. Because I have mean 0, if anything is ever unmatched, the integral is going to be 0 and it's not going to contribute. So everything has to be matched in pairs. This is where you start counting on your fingers. If you have anything matched in a triple or higher, it will give you a lower order contribution and it won't matter. So everything's going to be matched essentially exactly in pairs. And so it's how many different ways can I match things in pairs? Well, that's actually standard combinatorial quantity. If I have k objects, if k is even, say k equals 2m, it's 2m minus 1 double factorial. And in fact, that's the 2mth moment of the Gaussian. Not all of these matchings will contribute equally. And there's a lot of combinatorics that goes on. In this case, the only ones that matter is when things are matched in adjacent pairs. So this is matched with its neighbor, the next one is matched with its neighbor. Anything else, anything with a crossing doesn't contribute. So if you're doing random matrix theory, you would then want to look at different ensembles of matrices with different structures and see how that would affect things here. It's nice to see data. Here's 500 matrices. I'm choosing the entries from a Gaussian. Not a bad fit to the semicircle line. I'm choosing the entries from a Cauchy distribution. This is not a good fit. Why is it not a good fit? The Cauchy distribution does not have finite variance. You can have an argument over Beer as to whether or not the Cauchy distribution has a finite mean and the mean is 0. The Cauchy distribution is symmetric about the origin, so I'm willing to accept that it has a mean of 0. Technically, you'd want the integral of the absolute value of x times p of x to be finite. That's not the case here. But clearly it has infinite variance. There are issues. The GOE conjecture, which is actually now a theorem, is that if you look at the spacings between adjacent normalized eigenvalues, that converges to a universal distribution, which is approximately the following thing over here. And for a while it was only known if the matrix elements were chosen from a Gaussian. It's now known in much greater generality. So here I'm choosing my matrix elements from a uniform distribution, and we can see a pretty good agreement with the GOE distribution. Going back to the Cauchy distribution, good fit, bad fit. It's not horrible, but it's not terrific. But these are only 100 by 100 matrices. Over here, this was 300 by 300. So let's compare apples and apples. So if I do 300 by 300 Cauchy, that's not bad. So in some sense, the spacings between adjacent normalized events is the more natural thing to study. The density of states, that's allowed to vary. And in fact, different systems of matrices have very different density of states. But we believe that the spacings is universal. Another example to do is random graphs. So here I am looking at a graph, so I have a bunch of vertices, I have some edges connecting them, and I can construct an adjacency matrix. And these edges are undirected, so I'll put a 1 or 2 or 3 depending on how many edges I have connecting vertices I and j. If you want to think of this as you're building a network. And you might say, well, why would I waste resources and build multiple connections? Maybe it's extremely important that 3 and 4 be able to communicate. Maybe it's the president, and NORAD, and the president needs to be able to make sure messages reach NORAD. So you might want to have multiple ways of transmitting. This is a real symmetric matrix. We just talked about the density of eigenvalues and the spacings between eigenvalues of real symmetric matrices. But this is a very thin family of real symmetric matrices. So maybe it has different behavior because these entries have to be integers. An example people often look at is D-regular graphs, where each vertex is connected to exactly D neighbors. Oops, went too fast. So the main result is McKay's law that the density of eigenvalues for D-regular graph converges to the following. And so here's an example, I think, when D equals 3. When you see something like this, one of the first thoughts you should have is, let me take a limit as D goes to infinity. Let me see how the behavior changes. And so when I go up to 6, what is that looking like?
Just a square.
It's looking like a square. It's actually looking like the semicircle. So, it's not quite enough data to really see, but it is converging to a semicircle. If you look at what's going on, if D is really, really large, x is at most square root of D, essentially 2 root to D. So D squared minus x squared, this doesn't really matter anymore. And this essentially becomes D over D, it becomes 1 over D. And now x and D are comparable. And you can begin to see now it's converging to the semicircle. That this part over here that's causing all this change this strange behavior, that becomes insignificant in the limit. So you want to get a sense of limiting behavior. If you think about what's going on, as D becomes larger and larger and larger, you're allowed to be connected to more and more neighbors. And so in some sense, you're fattening up the ensemble of possibilities. Okay. Okay, good. And so the last one is spacings between adjacent eigenvalues. And if you look at spacings between adjacent eigenvalues, this was done by 4 people, including Stephen Miller, but not me, my compatriot of the same name, born same year, same city, also a student at Princeton. And so you see the spacings between normalized eigenvalues of D-regular graphs is looking like the GOE again. So you have this incredible universality. And to me, this is one of the exciting things about this field, is there's not that many possibilities for an answer. So if it was multiple choice, I think I would only have to provide about 5 possible choices for you. All right, so L functions. So this is the quick blitzkrieg review of L functions. So zeta of S is the most important of the L functions. It's the first one you often meet. It's the sum of 1 over n to the s, where n ranges over all the integers. It turns out it's the same as the product over primes. This is called the Euler product. It comes down to the fact that we have the fundamental theorem of arithmetic. Every integer can be written uniquely as a product of primes. Use the geometric series expansion, expand this out, and you'll see the two are equal. If I asked you to give me the next integer after 1,314,206, hard question or easy question?
Easy.
Easy. If I asked you to give me the next prime. So the idea is we know where the integers are. There is no mystery anymore in the distribution of integers. We understand the integers quite well. The idea is to try to use properties of the integers to deduce properties of the primes. And this Euler product links the two together. So we have a functional equation that relates the values of the zeta function at s and 1 minus s. It turns out to be useful to complete it by adding some gamma factors and some other stuff. And so when you're looking at L functions, you often put in these extra factors. The Riemann hypothesis is true. We don't have a proof yet, but it is true. All the non-trivial zeros have real part 1/2. The trivial zeros are at -2, -4, -6, -8, -10. They're well understood. And then the observation is that spacings between zeros behave like the spacings between eigenvalues of complex Hermitian matrices. And this was the original observation. It's been refined a little bit since then, but this is the start of the wonderful connections between the two subjects. Oops, going a little bit fast. So instead of looking at the Riemann zeta function, I can make almost no change by just replacing 1 with a sub f of n. And the question is, when does this lead to something interesting? And that's where you get different families of L functions. You might have seen Dirichlet L functions, quadratic characters, general characters, elliptic curves, different things over here. For the most part, we don't like things unless they have an Euler product. And you'll see in a few moments why the Euler product is so important. So this sum over integers is related to a product over primes. For each prime, I have some function. I have some kind of completed L function where I add in some gamma factors and stuff like that, and I have a functional equation. Different people have different normalizations. If you're looking at just elliptic curves, people sometimes have s goes to 2 minus s. It's a little bit more convenient to always normalize, so s always goes into 1 minus s. That way, you always know when you talk s equals 1, that's the edge of the critical strip. With some people with elliptic curves, that could be the center of the critical strip. The generalized Riemann hypothesis, or there should be a G there, is that all the non-trivial zeros, again, have real part 1/2. And again, you see the same behavior as you would see in random matrix ensembles. So here is a wonderful picture from Andrew Odlyzko, and it just really highlights this connection between number theory and random matrix theory. So I believe the solid line is the prediction from random matrix theory. The dots are what you get when you look at number theory. It might be the other way around. It doesn't really matter because the fit is that good. And this is looking at something at the 10 to the 20th zero. So this is a phenomenal set of computations. So the behavior of zeros of L functions are looking like the behavior of eigenvalues of matrices. And so for a while, people thought that the only matrices we needed to understand was complex Hermitian matrices. And that seems to describe everything in number theory. All right, how do we get our hands on quantities like this? Well, we saw for random matrix theory, the eigenvalue trace lemma was beautiful. It started the whole game. It allowed us to convert from what we want to what we have. So we want to have some analog of this. So anybody who has taken at least one class with me has heard me basically say you need to have a Pavlovian response whenever you see a product. If you are talking to a 10-year-old, you may resist your temptation because for them just multiply. But any time else, if you see a product, you should take a logarithm. Why?
Sums are nice.
Sums are nice. We have courses in sums. We learn how to deal with sums. We don't know how to deal with products. So you take a logarithm, convert to a sum, and then exponentiate at the end of the day. The other thing which is really nice in complex analysis is one of the big things to do is integral of the logarithmic derivative. And so if I take the logarithmic derivative, I can write the zeta function as a product. And the product is screaming for the log. So that's why I want to do it this way and not use the fact that I can write the zeta function as a sum over integers. I'll use that later, but right now here, this is a great way to get the primes into the game. So now I take my derivative, the log, everything comes through, and I get the following. So now I use the geometric series down below, and then whenever I have 1 over p to the 2s, 1 over p to the 3s, 1 over p to the 4s, those terms are going to be good, they'll be negligible, you can easily figure out what their contributions are. The difficulty is this term. As s goes to 1, this is a sum that has convergence issues. When s is near 1 over p to the 2s, that's absolutely fine. So now I integrate. And so when I integrate, I can choose what to integrate this against. Let's integrate it against x to the s over s. I shift my contour. The pole of the zeta function at s equals 1 will give me an x to the 1 over 1 with a negative sign because it's a pole. Negative times negative is positive. So the pole of the zeta function is going to give me an x. Everything else is going to give me like a negative x to the rho over rho. So if the Riemann hypothesis is true, this is going to look like x minus sum over the zeros of the zeta function of x to the rho over rho. That'll be size like x to the 1/2. It'll be much, much smaller. On the right-hand side, we have a very nice integral. And it turns out that if p is less than x, this integral is 1. If p is greater than x, the integral is 0. If p equals x, you've got to be a little bit careful. It is... So it's 0, I'm sorry, it's 1 if it is less than x. It's 0 if it's greater than x. If it equals x, 1 over 2. 1/2. All the answers are correct up to modulo factors of 1 over 2 pi I. Which you should have floating around on both sides. But if p equals x, you have some technical issues. So frequently when you're choosing where you put your contours, where you divide things, you might choose your values of x so it doesn't exactly go through something. This is just something to have in the back of your mind when you're doing calculations like this. Alright, well, I don't have to integrate against x to the s over s. I could integrate against something else. Let's take a nice test function phi of s. So frequently phi will be a Schwartz function. That means it's infinitely differentiable. It and all of its derivatives have rapid decay. So over here, when I now do the integral, I will get a contribution at the pole and then at the 0. So I'll get basically sums of phi of rho. Sums of my test function at the zeros of the Riemann zeta function. On this side, I have phi to the s times p to the minus s. Well, whenever you see something like p to the minus s, you want to convert it to an exponential. So this becomes, if I write s as sigma plus it, e to the negative sigma log p, e to the minus it log p. This is essentially a Fourier transform. It's a Fourier transform of a nice shift of my initial function. And if sigma equals 0, then this is really nice, I don't even have to worry about that term. And so now what I'm going to get is, I will get sums of my test function at zeros over here. I'll get sums of the Fourier transform of my zeros, of my test function at zeros over here. Alright. So you end up with explicit formulas. If you have the Riemann zeta function, this is what you get at the end of the day. If I have some nice function g, and if I let phi be its Fourier transform, and again, the definition of Fourier transform depends on who you're talking to. This is not the definition I prefer, but this was the book I was using. You can have a minus sign here or not. You can have a 2 pi I or not. Depending on how you put in these factors, some formulas become easier, some formulas become harder. And then I basically get a sum over zeros is related to something like this. More generally, I consider Dirichlet families. So I have a Dirichlet character chi. Maybe chi is going to go through conductors, all characters with conductor m. And I now get something like this. So h is my test function, h hat is its Fourier transform, and I'll get a sum of the zeros. And now there's a little bit of a difference. Instead of just summing over the zeros, I'm putting in a weight. And so I'm weighting the zeros. That's just a simple rescaling. Think of it as just changing your test function a little bit. Instead of using your function f of x, use the function f of 3x. And this is to normalize things so that my zeros near the central point have mean spacing 1. And so if I look at what I have over here, I now have this sum over zeros is related to the following. This piece over here is coming from the gamma factors from completing the functional equation. This is extremely nice. This is not hard to evaluate. There's no number theory here. These are the ones that are hard. They now involve sums over chi and sums over chi squared. It turns out the higher prime terms don't matter. And they're very small. What's nice here is, because my conductors are all constant, if I were to now sum this over all characters of conductor M, I could pass the sum over the family through my test function to the coefficients of my L function. And then somehow use knowledge of sums of the coefficients to deduce things about the zeros. Alright, so if I have cuspidal new forms, which I know a lot of you will be looking at, the formula is going to look the following. And so I'll have sums over here, which will be related to sums of the Fourier coefficients. And it turns out you can evaluate the sums of the squares, the prime squareds, without too much trouble. So this is where you just roll up your sleeves and you start doing the calculations. Alright, so some of the statistics we can look at. The first one is the n-level correlation. And so Montgomery was looking at the pair correlation for the Riemann zeta zeros. This is related to properties of the class number. He talked to the great Freeman Dyson, who told him that what you're seeing for the zeta function is very similar to what we see when we look at nuclear physics and random matrix theory. And so here I'm using a box. It's much better to use a smooth test function, and we can calculate what this answer is. The problem with that is that it's insensitive to finitely many zeros. So I can throw away, or I can add a couple of zeros and not really change anything. What's nice about the n-level correlations is I can go very high up on the critical line. Each L function has infinitely many zeros. The zeros get closer. There's enough to average over. But the most important point for L functions is the central point at s equals 1/2. If you think of families of elliptic curves, it's at s equals 1/2 that we have the action. We have a group of, the set of rational points is a group, and I can attach that to an elliptic curve, and I want to know what is the rank. It's some number of copies of Z plus some torsion group. There's only finitely many possibilities for the torsion group. The number of copies of Z is very mysterious and still very much open as to how that behaves. So we have a couple of results. Riemann and Katz-Sarnak proved the n-level correlation for automorphic cuspidal forms agrees with these random matrix theory things. And it looked like everything was being described by the complex Hermitian matrices. But then Katz and Sarnak noticed that if you looked at the n-level correlations of the classical compact groups, you get the same answer. And so what's the right model to describe what's going on for the zeros of L functions? Well, all these different families of matrices actually give the same answer if this is what you study. But all of these models, when you're applying them to what's going on at the central point, they'll actually give you different answers. So you want a new statistic. You want a statistic that actually cares about the zeros at the central point. And this is going to be the low-lying zeros, the zeros near the central point. That's what a lot of us are going to be studying in the near future. And so we want this new statistic. And so here's the definition. And again, exactly how you define it is up to you, but it changes the combinatorics a little bit. So phi is going to be a test function of Schwartz test function even. The zeros turn out to be symmetrically distributed about the critical line. So if you take an odd function, it's going to just trivially vanish. I'm going to rescale the zeros by something called the log of the analytic conductor. Because this is rapidly decaying, only the zeros near the central point really contribute in the limit. Most of the contribution is from these low zeros, but now I only have a couple of zeros for each L function. So now I have to average over L functions in a family, L functions that behave similarly. And the idea is by averaging over similar curves, I can now get something that will exist, that there'll be some nice limit. Okay. So the Katz-Sarnak conjecture is that for a nice family of L functions, the limit exists and it agrees with a classical compact group. So, a little bit more explicitly, here are my zeros, I rescale, I sum over all my indices, I then sum over all the forms in my family, I divide by the number of forms in my family, and then I let the family go off to infinity. So maybe I'm looking at Dirichlet characters of conductor M, and I let M go to infinity. I'm looking at cuspidal new forms of level n, and I'm letting n go to infinity. You have some parameter going off to infinity, so you're getting more and more forms in your family to average over. And the hope is that in the limit, this will agree with integrating your test function against some density that's associated to the different classical compact groups. Okay, so here are the answers for the different classical compact groups. It turns out sometimes it's easier to look at the Fourier transforms of these densities rather than the densities themselves. This is unitary, delta naught is just the Dirac delta functional, symplectic, and then the three orthogonal flavors. And what's interesting is this is the Fourier transform. So I have the integral of phi times w is the same as the integral of phi hat times w hat. This is either Plancherel or Possible. I always forget which one goes which way. And so the problem is, if my test function phi is such that its Fourier transform has support between -1, 1, that means it's 0 outside of -1, 1, I can't tell the difference between the three orthogonal flavors. These functions are all equal between -1 and 1. So for instance, this function is equal to 1 if u is less than 1. So if u is less than 1, this is negative a half plus 1 is a half, a half, a half. These three functions look the same. If I can calculate these integrals where the support is greater than 1, then I can distinguish the three orthogonal flavors. So you could have the ridiculous situation where you have a family of L functions. Every L function has odd functional equation, but the family looks like it has even symmetry. You know, that shouldn't be the case, but you can't tell the difference just by looking at the one level density. Alright, so here is a quick conversion table between number theory and physics. So I actually learned a lot of my number theory from a nuclear physicist, so I speak number theory with an accent. More than just the Boston accent. So in nuclear physics, you study energy levels. In number theory, you study zeros. In physics, you smash things by shooting neutrons at things. We're a little bit more civilized. In number theory, we shoot Schwartz test functions. Okay? And we evaluate the sums. In nuclear physics, you would love to be able to shoot a neutron of arbitrary energy level. But we don't have the physical ability to build a system like that yet. We can only shoot neutrons with a certain energy band. And so from that, we can get partial information about what's going on. It's the same thing in number theory. We can only evaluate the sums if the Schwartz test function is supported in a certain regime. If we could shoot in an arbitrary function, we would love to shoot in the Dirac delta functional. And then that would tell us exactly what's going on at the central point. You would prove the Birchman-Dye conjecture, you would make $1 million, you'd take me out for lunch, hopefully at a nice restaurant. Actually, I don't care about nice restaurants, I'd rather have the cash. But we can't do that. We can't evaluate the resulting sums because the Fourier transform of the Dirac delta function, the spike at 1, is the function that's identically 1. So the Dirac delta function is perfectly concentrated. So this is a duality principle that there's if you look at the support of your test function and its Fourier transform, the product of those has to be at least a certain amount. In other words, you cannot arbitrarily localize well both a function and its Fourier transform. Does this remind you of anything from physics?
Heisenberg.
It's the Heisenberg, yeah. The Heisenberg uncertainty principle is a mathematical statement. Well, okay. There's a mathematical statement that you cannot localize a function and its Fourier transform simultaneously too well. The physics is that, for some strange reason, a function and its Fourier transform correspond to position and momentum operators. That's where the physics comes in. But it's really, Heisenberg uncertainty principle is really a statement about a function and its Fourier transform. And so we would love to understand what's going on for the zeros at a specific place, but then that means the resulting sum over the coefficients of the L function would have to be over an extremely large window. We can't evaluate those. I have some results which I'm going to blow through. We have results for lots of families. We have results that I've done with lots of my colleagues. A lot of them were at Michigan, which is why they became in blue. The main tools are controlling the conductors, having some kind of explicit formula, and having some kind of averaging formula. And the averaging formulas are often hard to work with, and depending on what we have, it'll be harder in some cases than other cases. Okay, so one application, which I'm not going to go into too much here, I'll leave it on the slides, is you can use this to bound the order vanishing at the central point. And that's one of the things people care about is how often do you vanish in a given family. The n-level densities allow you to do stuff like that. Alright, So let's end today by doing an explicit example. Let's calculate the low-lying zeros of Dirichlet L functions. And so we're going to start off with characters. M is going to be prime. I can't use P because I have P as a prime in the sums that arise, so I will use the letter M. So I look at Z mod MZ star. This is a cyclic group of order m-1, and it turns out it has a generator. So I will admit I have never taken a class in abstract algebra. I have picked up a lot of it by osmosis. This is the level at which we need it. We can make things very explicit in this case, which is nice. So here is the m-first root of a unity. And then the principal character chi naught is 1 if k and m are relatively prime and 0 otherwise. And then we have m-2 primitive characters that are determined by their action on the generator G. So once I know what it does to G, because the group is cyclic, every element can be written as G, G squared, G cubed, G to the fourth. I only have to figure out what's going on at one place. So I can write K as G to the A, modulo M. And so chi L of K will be the m-1 root to the L power. So each character is essentially just raising it to the L power. Alright, so everything is really explicit. So we have these Gauss sums, they have size square root of m. We have my L function, so it has a product like this. When you expand it out, you'll have a sum of chi of n over n to the s. We have the completed L function. You have to worry about, depending on the value of chi of -1, whether or not epsilon is 0 or 1. Doesn't really matter. There's some kind of completed L function. The explicit formula then reads the sum of my test function at the scaled zeros is low. This is coming from the p cubed, p to the fourth, p to the fifth. These, we can figure out what their contribution is. This is coming from the gamma functions. This is just going to be phi hat of 0. And then we have a sum of the character and the character squared. And that's what we need to figure out. So we're going to now want to sum over all Dirichlet characters of a given modulus. Well, that's fine over here. These are all the same. And because they're all scaled the same way, I can pass the sum over the family through all of this to these. And now I can use orthogonality relations. More than that, I can actually do things explicitly because I know what these characters are. And so what we can do now is, I have the sum over all my characters, and I'm going to want to just move this part over here through all of this to over here. Okay. Any questions on where we are so far? We have about 5 minutes, should be able to make it. So character sums. If I sum a specific value of k over all characters, it's equal to 0 if I'm not congruent to 1 mod m, and m-1 if I'm congruent to 1 mod m. And the reason is, if my character is being evaluated at 1, I always get 1 by multiplicativity. Chi of 1 squared is chi of 1 times chi of 1. And if it's not being evaluated at 1, it's going to just average out and wash away. So this is a really nice formula. Unfortunately, we're not summing over all characters. We're summing over all characters that are in principal. Fine. I can take into account trivially what's going on for the principal characters. Not a big deal. The question is, why do I want to write it like this? Well, this way I can write it as, there's always this term -1. And then there's this extra factor of m-1. Now what's interesting is, this extra factor is enormous, but it happens really. It happens only when the prime is congruent to 1 mod m. So every now and then you're going to have a huge boost. But it's more then than now. Okay, so we substitute that into our formula over here. We pass this sum over here, and we just execute the sum over p. Now we might have to worry if p actually equals m, but that's only 1 prime, not going to make a huge difference. And so now we have a sum. We have two possibilities. This is the -1 that always came into play, and then this was the m-1. So notice here that m-1 over m-2, this is quite large. The m-2 over here is because we're dividing by the number of characters in my family. Each one is given the same weight. So over here, this term wants to be small because I'm dividing by m-2. This term, unfortunately, wants to be quite large because this number here is now of size 1. The advantage here is that p has to be congruent to 1 mod m. What can you say about the smallest prime congruent to 1 mod m?
Well, it's at least as big as, it's bigger than m.
It's bigger than m. It's at least m+1. And so since it's at least m+1, the very smallest term I could have is 1 over the square root of m+1. So I will have at least some decay from that. And now we sum over all primes from 2 to m to the sigma, or all primes congruent to 1 mod m up to m to the sigma. The larger sigma is, that means the greater support we can take for the Fourier transform, which means the more we can localize our initial test function, and the more we can deduce about the zeros. So the larger sigma, the better things are. So we want to evaluate these sums for as large support as possible. Well, if we just trivially estimate, so this means up to some constant, the log of p over the log of m, best case is this is going to go m to the sigma, so this will be of size sigma, sigma is fixed, this is going to be some universal constant. My function phi hat is Schwartz, it is of rapid decay, it's bounded, so this is going to be most p to the minus 1/2, p to the minus 1/2, but a sum of p congruent to 1 mod m. So to try to figure out how large this can be, I can replace sums over primes with sum over all integers. I'm losing a logarithm here, I'm lazy. I can do a little bit better. So this sum over here, how large can this be? Well, if I integrate this, I'll get k to the 1/2 over 1/2. I'll get an m to the sigma over 2. So basically, if sigma is less than 2, this is going to be insignificant. This one I've got to be a little bit more careful about, but I have k is congruent to 1 mod m. So the easiest way to handle this is to say, well, look, let's look at this sum over k congruent to 1 mod m, k congruent to 2 mod m, k congruent to 3 mod m, etc. Of all of these progressions, the one that has the smallest total sum is when k is congruent to 1 mod m. So if I replace this sum over 1 mod m with the sum over all k, I get to divide by 1 over m. And now again, that's exactly the same sum as this, and so if sigma is less than 2, I'm okay. We now look at what's going on with the squareds. So again, with a little bit more work, you can now figure out what's going to happen with these squareds. We have plus or minus 1s. Things become a little bit more involved. We now get sums like this. And so now if you look at this sum, what can you tell me about the sum of 1 over k when I go all the way up to m to the sigma halves? It's basically going to be a log. And so in terms of the contribution of this, it's actually going to be much better. I think I actually dropped a giant parenthesis that should be going around all of these. And so I'm going to have a 1 over m here, I'll have a log m over here, I'm fine. So in fact, the second sum is actually doable for any support. Okay, so now this is just going through, let's let m be square free, and in fact one of the things I'd like to do this summer with some of you is remove the assumption of square freeness. And this is just trying to go through the different ways of handling square free m. So I'm not going to go through the details here, but you can go through and you can see without too much work, it will eventually come in. And you just have to do some careful counting. And we're able to get a contribution from, if you have a square free integer that's odd with exactly r factors, this is how much the first sum is, this is how much the second sum is, and then you just need to know how many square free numbers have exactly r factors. Okay, so this concludes part 1 of the talk. So this is a lot of stuff to digest. We can do the lecture on part 2. So part 2 is the more technical, gory details. And so I'm happy to go through this part tomorrow.